Hello, and welcome to Lecture 3 of Electric Interactions in Phys 1204. This lecture is all about a very important phenomenon called polarization. Our overall goal in this lecture is to understand something that we saw right at the very beginning of Lecture 1, but which is probably not clear to you. You've seen that opposite charges attract and similar charges repel. Well, naively then, you might expect that charged objects would exert no force at all on neutral objects. But that's not at all what we see. We see that all charged objects, whether they're positively charged or negatively charged, attract neutral objects. Why? This rather simple device is called an electroscope, and when I bring the plastic rod near it, you see that it disturbs the needle. Here's another slightly more sophisticated electroscope, and again, when I bring a charged object near to its bulb, such as the wool or the plastic rod, it disturbs the needle on the electroscope. An electroscope is useful for demonstrating several things that we need to understand. So let's understand how an electroscope works. Some terminology is useful. At the top of the electroscope is a bulb or plate, and attached to that is a post. And hanging from the post is either a needle or a thin piece of foil called a leaf. All these parts are made of metal, and very importantly, they're all insulated from the surroundings, so unless we transfer charge onto the electroscope, it will remain neutral. The needle or the leaf normally hangs parallel to the post, and by normally I mean when the electroscope is neutral and no charges are near it. But when we place a negative charge, like the plastic rod that I just demonstrated with, near the bulb of the electroscope, because the electroscope is metal, the electrons in it are mobile, and so the electrons are pushed downward in the electroscope. This leaves the bulb positive, and the post and needle are now negative. And because the post and needle are both negative, they repel each other, and so the needle stands out from the post. Notice that the electroscope is still neutral overall. We haven't added any charge to it, we've just moved charge around on it. We've separated the charge. We call this polarization. We say that the electroscope is now polarized. Incidentally, we can do the same thing with a positive charge, and the opposite will happen. It will pull electrons up from low on the electroscope into the bulb. So now the bulb will be negative, and the post and needle will be positive, and again they'll repel each other. Understanding polarization turns out to be the key to understanding why charged objects attract neutral objects. Let's think about the familiar situation of a charged plastic rod being brought near a neutral metal ball. As the rod is brought close to the ball, it repels the electrons in the ball. And because the electrons in the ball are mobile, because the ball is made of metal, they'll tend to move away from the rod. The result now is that the side of the ball facing the rod is overall positively charged, and the side facing away from the rod is overall negatively charged. The ball is polarized. The rod will exert an attractive force on all the positive charges in the ball, and it'll exert a repulsive force on all the negative charges in the ball. But we know that electrical forces decrease in magnitude with distance. And so the repulsive force on the negative charges is smaller than the attractive force on the positive charges. As a result, the total electrical force that the rod exerts on the ball is an attractive force because it's just the vector sum of the force on the positive charges and the force on the negative charges. It's time for a question to check whether you're following along. So suppose that instead of using a negatively charged rod to polarize a ball, we bring a positively charged rod close to a metal ball. So which of these four diagrams is the most correct representation of how the charges will be distributed on the metal ball and the sizes of the forces exerted on it?